We turn our attention now to the energy that an object has simply because it's rotating, even if it's not moving from place to place. It's just rotating in one position that has energy there. This continues our pattern of looking at things for rotational motion on the same lines as we did for translational motion. So we started in either case with kinematics, then we moved on to conditions required to have no change in either linear motion or rotational motion, and then we looked at what causes changes, either a force or a torque for linear and for rotational motion respectively. And then we looked at conservation of energy with translational motion and kinetic energy in particular. And now we're looking at kinetic energy again, just for a rotating object. How do we know a rotating object has energy? Well, because we have to do work to make something rotate. Think about the basketball spinning on your finger here. In order to get it spinning, you have to apply a force to the edge of the ball and over some distance. You do work on that basketball, and so the basketball must be gaining energy due to that work. And it's, in this case, rotational kinetic energy. Now really this isn't any different from the kinetic energy we've worked with in the past. We just have to think about individual pieces of our object. So let's say we have a ball that's going to be rotating. Let's look at just one little chunk of the ball right on the outside. And we'll say this whole thing is rotating in the clockwise direction. So if I watch this little piece here, it's going to rotate all the way around the ball here, going around and around in circles. It's going to have some speed, and that little chunk has some mass, and so we could figure out how much kinetic energy it has with k equals 1/2 mv squared. Now the mass, that's only a part of the ball, so we'd have to do that for every single one of these little parts. And if we looked at, say, another part that was in a little closer to the center, that's going to be going around in a smaller circle, still making the same number of revolutions per second as this outer one, but it doesn't have to go as fast, so it'll have a smaller speed. And we do this for every little chunk all the way along this ball. We solve that with calculus, or we've actually derived simple equations for this. We can do the rotational kinetic energy as 1/2 times the rotational inertia times the angular speed squared. So rotational inertia, that took care of our mass distribution idea, and as we looked at before, that's actually derived with calculus as well, so you can kind of see the parallels there. And then omega is a better variable to use for rotation, because the outer dot here and the inner dot, even if they're traveling at different speeds because they're different distances from the center, they won't have different angular speeds. So it's still the same number of radians per second or revolutions per second or per minute for either one of those two spots. So omega is a good unit to use on this one. The units for kinetic energy are still going to be joules, and the units do work out here with the units of I and omega. So let's turn to an example problem now. In this problem, we'll look at a bike wheel, and we're actually told here to treat that bike wheel as though it's a cylindrical hoop. The fact that it's being treated as a cylindrical hoop gives us information about rotational inertia. So if we look in our textbook, we have this table of values for rotational inertias based on the shapes. For a cylindrical hoop, the equation is just mr squared. So that's what we're getting from that piece of information. We're looking for rotational kinetic energy, so ultimately k rot. Rotational kinetic energy is 1/2 I omega squared. So I need to know the I value there, and I need to know omega. Well, let's start with I. The rotational inertia is going to be equal to the mass, 1.0 kilograms, times the radius is 0.35 meters. It's 70 centimeters for the diameter. So 0.35 meters for the radius squared. And so we get a rotational inertia there of 0.1225 kilogram meters squared. Next we look at omega. Omega is actually given to us, but it's in weird units here. We've got 85, and that's in rotations per minute. Now, I don't want rotations per minute. I want radians per second. So let's do a conversion here. So first off, we want seconds, not minutes. So there's 1 minute for every 60 seconds. And then I don't want rotations, I want radians. Well, for every 1 rotation we make, we have 2 pi radians. So rotations are going to cancel and minutes are going to cancel here. And we'll be left with the units of radians per second. And on this one we get an answer of 8.9 radians per second. So then we come back to our kinetic energy equation. Rotational kinetic energy is 1/2 times 0.1225 kilogram meters squared times 8.9 radians per second, and that gets squared. So we end up with a rotational kinetic energy here of 4.85, and the units on that are joules we expect for energy, but let's just double check that. We've got kilograms and meters squared, and then when we do the radians per second and that gets squared, we'll have radians squared per second squared. So we end up with kilogram meters squared, radians squared per second squared. Keep in mind, radians are the weird units where the radian is really just a placeholder. There actually aren't any units on that number. It's a ratio between circumference and diameter. And so here we can sometimes just get rid of the radians since it's just a placeholder there. So if we get rid of those, we get kilogram meters squared per second squared, and that is the long way to write joules. So that's our rotational kinetic energy. There's a second part to this question, kind of a throwback to our energy and power stuff. So let's figure out what the power output of this motor is if it takes 4 seconds for it to get up to that speed. So just as a refresher, power is equal to the change in energy divided by the change in time. In this case, our change in energy, we're adding 4.85 joules to that bike wheel. Initially it had 0 rotational kinetic energy, now it has 4.85 joules of kinetic energy. And it took 4.0 seconds to make that happen. And so in this one we're going to have an answer of 1.21, and the units on that are joules per second, or watts. A 1 watt motor, not a very powerful one there. Doesn't take very much energy to get that spinning the way that it is. So if it takes a full 4 seconds to get it going there, that's not much of a power output on this one. So that's rotational kinetic energy. Where this problem, or where this idea gets interesting, is when we apply this to conservation of energy problems. In particular, when we have multiple types of energy, maybe kinetic energy of translation and kinetic energy of rotation interacting somehow, maybe for a rolling object. So that'll be addressed in the next video. Thanks very much for watching. If you found this useful, by all means like it and make it easier for other people to find. And if you think future videos will be helpful for you as well, please subscribe to the channel.